Good day, and you're all very welcome to this week's technical session of the CNPS, hosted by me, Ian Cowan. Now, we're very happy today to have back with us James Keene, who is one of our regular participants in our technical sessions and also our Sunday cosmology sessions, which are hosted by Harry Ricker. So, Jim is a dab hand, I think, at some of these procedures. We've just been doing a little rehearsal for the last 5 minutes, and we haven't had any problems. Jim is actually resident in a most propitious place on the surface of the earth, Dominica in the Caribbean, where I think the climate contrasts most significantly with what I have to put up with in the land of perpetual winter, Hibernia. But anyway, so now the talk today will be on Jim's binary mechanics, which is his major catch-all system for what he's been doing in various branches of physics. And I understand, I may not be totally accurate here, but I think I asked him very briefly what the binary signifies. And he's looking at these elements of discrete space, which can either be full, in other words, they'd have a 1 there, or they could be empty, in which case they'd have a 0. But Jim will explain that more. And in particular, he's drawing this into looking at cosmological models. So he says that binary mechanics cosmology today, and cosmology is the subject of our Sunday sessions, as I said earlier. So many phenomena predicted and demonstrated by binary mechanics have implications for building a successful, I think, cosmological model has been cut off there. But more specifically, Jim gave us an element where you would have two parts. The first part would be the proposition that cosmology modeling must be based on a successful theory of everything, TOE, such as binary mechanics. Binary mechanics is a TOE, is discussed. And then the second part of the presentation would be the second part of his contention. Many phenomena predicted and demonstrated by binary mechanics have implications for building a successful cosmological model. Right. So I'll bring Jim up in a second. I don't think we should have to put the direct link in. Yeah. Okay, that's fine. Yeah. So yeah, I just paste Jim there, just a note on that. But what we'll do is we'll give Jim whatever time he just wants to be reminded towards the end. I might interrupt and say, Jim, you've only 10 or 15 minutes left, so he can pace it. And he knows that he's free to take an hour or an hour and a quarter if he wants, or 55 minutes. It's not very strict, but we always like to give maybe up to an hour for the questions and answers and discussion. Most of the questions actually coming in, I'm not complaining about this. If you wish to do that, that's fine. But most of the questions coming in on Facebook and StreamYard are just really discussions between people. So we don't specifically advert to them. But if there's any specific point that you want me to raise with Jim, just put this is a question for Jim, so I don't miss it, because otherwise I'll think it's just group chat or something like that. And then we'll bring people in on the green room. We should have people coming in on the green room, and we can have a fuller discussion on matters. And as I say, we normally try not to interrupt the speaker, and we'll deal with everything at the end. But if there's anything really very, very urgent, you just didn't understand what he said, or what was that word or something, just put a note in. This is urgent, and I'm sure Jim would forgive us if we do have to interrupt him and say, sorry, we didn't understand that word. What did you say there? Right. Now, so Jim, good day to you. Great to have you.
Hello. Hi.
And so what I'll do is I'm going to bring myself down, but I'm in the background, obviously. So if you need me, just shout. And shall I bring the slides up now, or would you?
Yes, please.
Let's see. So let me see. Okay. and you're quite happy with that. Some people may wish to maximize it in their own system, but we'll leave Jim's photograph up there, so it'll be more like a live lecture, real face-to-face lecture where you see the speaker. But I'm going to bring myself down. What was that, Jim?
I said that sounds great, Ian.
Excellent. So I'll do that now, and I'm going to give you complete control of the floor and everything else. And just call me back if there's anything you wish.
Okay, today I'd like to humbly submit for your consideration 2 ideas. One is that a successful cosmological model should be based upon the best theory of everything that we have. So my presentation today will have 2 parts, as Ian indicated. I want to talk a little bit about the theory of everything known as binary mechanics and why I think it's the best, and then use the equations of binary mechanics to cook up a universe for everybody's enjoyment. Okay, so let's start with the first slide. Historically, binary mechanics developed from what is now I call antiquated, outdated quantum mechanics, which has a lot of erroneous ideas in it, such as position uncertainty, Heisenberg's uncertainty principle, and so forth, and how I developed binary mechanics from that. As you probably know, there's a complex amplitude is used to compute probabilities of events, whereas binary mechanics allows you to compute exact values for events. So I took the complex amplitude, and here we have divided a complex number into various parts. If we take the absolute value of x and y and quantize them to quantize energy, we get 2 equations. These are the first 2 equations of binary mechanics. M equals 0 or 1, that's a binary number. L equals 0 or 1. Now, the math that you need to master in order to understand binary mechanics is only this single digit binary number, 0 or 1, something or nothing. Secondly, the AND function in AND logic, and the NOT function. And any 3-year-old who has mastered language, these 3 math ideas are built into language. So any 3-year-old has already mastered the yes or no one bit binary number, 0 or 1, to the AND function and the NOT function in just speaking a language, so that you already know the math. So I don't want you to think, oh, we have all the complex numbers, and gosh, I don't understand the math there. You don't have to. This slide is just showing you the origin of where we started to get the more simplified version that you're going to find in binary mechanics. Now, Planck wanted to quantize energy. That was a lifetime goal. He never achieved it. The closest he got was his Planck's constant H, so that now in binary mechanics, we fulfill that wish that with these 2 equations, M equals 0 or 1, and L equals 0 or 1. So there's 2 kinds of quanta or states which comprise the spot unit. Now, the spot unit then gives us a model of a space. And if we combine 3 spot units in a 3-dimensional fashion as shown below, we're just going to call it a spot. And the word spot, it just means a place where something is, right? So that's why we call it a spot. And the spot unit is a part of a spot, as you can see. We then find that there are different permutations possible in this complex amplitude. You notice we're not throwing away any information in the complex amplitude of the outdated quantum mechanics which binary mechanics replaces. but there are 8 particles can be uniquely defined by 3 binary values, the sign of X and Y, and the position swap. So if we just reverse the direction, like we see here, here are 2 spot units, the red and the green one, pointing in opposite directions. We get 8 elementary particles. Let's see what we have next. Okay, binary mechanics gives you an absolute reference frame. Definition: in physics, a reference frame is a set of coordinates used to determine properties like position and velocity. A frame of reference, or reference frame, this is just review, folks, is an abstract coordinate system whose origin, orientation, and scale have been specified in physical space. Third, an absolute frame of reference is some fixed reference frame that every observer in the universe would agree is at rest at all times. With full quantization of and the primary length constant L, binary mechanics defines an absolute reference frame. This is an important starting point here. The binary mechanics absolute reference frame enables study of the composition of and properties of objects such as electrons and protons with zero motion, where the velocity is zero, which occurs at 0 Kelvin temperature. I'll talk a little bit more about that as we go along. Point 2, absolute linear and angular momentum of any object or observer. Note that a reference frame is a perspective that one uses to determine if an object is moving. So we have an absolute reference frame, and then we're going to put some things in there. But let's finish up on our notion that binary mechanics is a successful theory of everything. Point 1, unsuccessful TOEs and cosmologies require input parameters based on unexplained measurements, such as the velocity of light c, the elementary charge E, Planck's constant H, the mass of the electron and proton, etc. Considering hundreds of proposed TOEs, I read recently that every single physicist has their own TOE. Well, that's impossible. If a TOE is correct and complete, there is only one. There couldn't logically be any other number of TOEs than one. Think about that. Only binary mechanics has derived the measured values of so-called fundamental constants. Point 2, incomplete TOEs and cosmologies lack a useful model of motion mechanisms, of how things move. That's supposed to be what physics is all about. Descriptions of motion, such as Newton's mechanics, are an important first step. However, motion descriptions are not equivalent to knowledge of motion mechanisms. You can describe velocity, acceleration, torque, etc., but not how. But those things don't tell you how something moves. This is very important. Binary mechanics has provided the best understanding to date of how things move. Thus, at present, binary mechanics is a leading TOE available for cosmological modeling. Now, these 2 points I have slides on. Here is the physical constants derivation tree. With full quantization, we can quantize energy in kilograms, italics capital M, length, which is about 3/4 of a femtometer, 2/3 of a femtometer, and time, which is a very small value there. The arrows show a tree where these values give you Planck's constant, electron rest mass, vacuum light speed, elementary charge, intrinsic electron magnetic moment, intrinsic electron and proton spin, which of course comes from Planck's constant. So, and not only that, we have the electron EDM is determined to be equal to 0, which is in agreement with experimental data. And the proton EDM, this is very controversial now, that's the electric dipole moment. Sorry, I didn't say what EDM was, is greater than 0, which is challenges a lot of what I call outdated theories in particle physics, the fact that the proton EDM is greater than zero. So that was point one on our previous slide. Point two on our previous slide is that the mechanisms of motion, and here we have an elementary particle flux and motion tree, where we can see that there are lepton d-quark transitions. This is the holy grail in particle physics, okay? The spot cube that I showed you in a previous slide indicates that electrons, which is the left-handed E here, can go to the right-handed d-quarks in a matter-to-matter exchange in both directions, as well as the right-handed electron, which is the positron, and the left-handed d-quarks, which are the antimatter d-quarks. And these elementary fluxes that are possible can then be give you a tree as to particle motion. There's a second basic discovery was the quark anti-quark transitions, which are denoted here, where d-quarks of the right-handed variety, which are the matter ones, can interchange, if you look at that spot cube that I showed previously, with the left-handed d-quarks, which are the antimatter ones. These elementary fluxes give you a tree where you can actually derive possible particle motion events and the mechanisms by which they occur. So that particle interactions in sort of what I call old-fashioned physics have been used to define forces. In binary mechanics, we can actually derive what are allowable particle interactions and get a whole tree, including the so-called weak force interaction, and find out it's not even a force at all. So that's my comments on particle flux and motion. Now there's points 3 and 4 to back up the idea that cosmology modeling must be based upon a successful theory of everything. Third point, binary mechanics is the only toe that I am aware of based on study of full quantization and its consequences. Everybody else believes that space and time are continuous. In other words, you have real number coordinates, you have an infinite, in any volume, you have an infinite number of points, and that somehow magically there are mechanisms at every single infinitely numbered numbers of points that actually carry out the physics that we observe, which actually is equivalent to a miracle, stating that miracles occur. Anyway, let me continue on. Binary mechanics reveals that a vacuum is not empty. B, recognized particles such as electrons and protons account for only a small percent of the energy content of a spatial volume. Old-fashioned views think that if you don't have any protons or electrons or any particles, you have empty space. C, popular gravity theories fail by omitting this missing mass, but it's there in binary mechanics. Binary mechanics provides previously unavailable technology to study vacuum content. This is a very important point. And the last one, point 4, bit function analysis. The bit function is simply the distribution of one states in the structured space, which is a three-dimensional lattice of spot cubes that were shown on a previous slide. So that is your bit function. That replaces the wave function in quantum mechanics. Bit function analysis technology based upon binary mechanics provides details of A, intrinsic angular momentum in the 2011 discovery of proton and electron bit cycles. B, detailed account of motion mechanisms, provides frame-by-frame steps involved in all particle motion. In the recent assassination attempt of a U.S. president, many investigators were doing frame by frame analysis of videos to try and figure out what was going on. For the first time that I'm aware, we have a technology now in bit function analysis where we can analyze with greater spatial and temporal resolution possible by any other technology, frame by frame, the steps involved in particle motion and basically all physical events. For example, the cesium-133 clock. Imagine you could study frame by frame its change of states in one clock tick. This is what bit function analysis can do for you. So let's look at some details about points 3 and 4 here. Here we have a graph showing if we start with the Binary Mechanics Lab software simulator, which can simulate systems in a volume of space, we can see the initial volume with 0 up to 100% of the locations, the M and L locations I pointed out to you in the spot unit, with 1 or 0 bits. At 1 up here maximum, they're all in the 1 state. They all contain a quanta, which is just a word, a label that I use to designate a 1 state. Now you notice that if we calculate the number of particles and their mass the final state is when this gets cooled down to 0 Kelvin. In other words, if we allow any 1 state quanta leaving the simulated volumes to just disappear, to not be accounted anymore, we're basically cooling the simulated system down to 0 Kelvin. Here we can do this in simulation, whereas we can't do this in real life because there's always going to be some 1 state quanta entering no matter what we try. So we get very close to 0 Kelvin, but we can't actually physically get there because we can't simply block out all of the incoming 1 state quanta, which would heat the volume back up. But so here's our final density then. Now, what do we have here? Here is the total, the blue curve is the total, including particles. If we take out the particles, electrons and neutrons and protons, we have a huge amount of particles of quanta still left. This whole area under the red or pink curve here is your final state at 0 Kelvin, which shows that vacuum is simply not empty. Now, what is this point here on the right? I'm going to come back to that, so keep this point on the right. This represents a massive explosion. The explosion is so massive that we wind up with a final density less than the threshold, which is about 0.07, less than the threshold for creating a proton. And so that's our supernova explosions there. Just keep that in mind. We'll come back to that. Okay, the point 4 was the Binary Mechanics Lab software represents methodological advances. The calculation ability of precise values, as I already mentioned. Vacuum studies, we can study perfect vacuum, which is not empty space, as I pointed out. 0 Kelvin states, which are the ground state particle definitions. It's ideal for light speed measurements and so forth. Parameter derivations, proton-electron mass ratio. It turns out that when we do this, we find out that the proton-electron mass ratio, by the way, is not a constant. It's supposed to be about 1,836.15 according to the NIST standards. But actually, that's only at a certain overall quanta density. And if you increase the quanta density, the proton mass actually increases for a period of time. And so that all of this work on gravitation based upon mass, which is largely nucleon mass, protons and neutrons, is sort of very questionable in view of these sorts of findings. We can also derive the alpha coupling constant, which is, and the vacuum light speed and so forth. We've done laser light simulation. The L bits, the L-type quanta appear to be magnetic monopoles. I'll just leave that there for you to think about, because that's not our subject for today, actually. So bit function analysis is all of the above. Let's move along here. So we have completed part A of the talk, which is we're going to use binary mechanics as the best theory of everything that at least I'm aware of at this point in time. And now we're going to make a universe. We have an absolute reference frame, as I already mentioned, and now but we need a place to put things. That's point one. That place is the spot unit. Now, the spot unit is more than a volume to put things. It contains all the parts needed to implicate the time evolution laws, which are equations 7 through 17 in the binary. There's a paper called Binary Mechanics Postulates, which you can read and see the exact equations. I have them on a slide if someone wants to look at them. These things, these parts, in other words, the spot unit is not only a spatial volume, as pointed out, it must contain parts which actually accomplish these time evolution laws. And these might be guides. For example, here is a blank white wall here. This means that a quanta can't go through that way. Valves, the strong force input and output are valves where a quanta can only go out here or in to this volume for the positron spot cube. In other words, why are there four of them here? Well, it turns out that in an analysis of the spot cube that I showed you earlier reveals that there are actually four kinds of spot units or arrangement of parts needed to implement the time evolution laws. And so, for example, with the electron, we have the strong force being input on this wall of it in the M bit, which is also called the might, just to have fun with words, and light for this is more the matter one, so we're going to call it a little might. And then this is the radiation one, which is the L type bit. And so that we have valves. And then for the equations of binary mechanics, we're also going to need sensors. And those sensors are shown as the legend down below shows here in blue and in green, where we need to sense neighboring states in neighboring spot units in order to determine what's going to happen in terms of the evolution laws of binary mechanics. So now we have a place to put things, and we realize that the story is not over. We still don't understand exactly what the machinery is here. We can figuratively say that we could maybe even build these spot units like a model that we could put on the table, and it might have various springs and ratchets and pulleys and gears and what have you, and we could say, hey, I built a model of the spot units which will do exactly what the laws of binary mechanics say should happen. Now, that's just figuratively speaking, an analogy. Really, if binary mechanics is the only valid toe in the shop that we have today, really then the next frontier in physics research is to study these spot units and exactly how they work and what parts they in fact have. That's where the state of the art in fundamental physics is, according to binary mechanics. So let's continue building our universe now. That's what this is. That's part 2 of our talk. Okay. 3, we discovered in 2011 intrinsic angular momentum in 2 cycles, which I call bit cycles, referring to quanta cycling. This was discovered simply by doing a simulation with only one single location, say the one I'm looking at here, the circle indicates an M type quanta. Let's set that to 1. And everything else is 0 in the total volume we're simulating. What do we observe? We observe that after a few cycles of implementing the time development laws, this quanta goes around in a circle and winds up just where it was in the first place. In other words, it's a bit cycle. Same way with the proton bit cycle, which is a larger bit cycle. And I discovered just recently, in fact, while I was making this illustration, so that if you want to make some discoveries in binary mechanics, just start writing some tutorials on binary mechanics and making illustrations. You'll probably make discoveries hand over fist. That the proton bit cycle is actually in the opposite direction. This gray dot in the middle here is the axis of rotation, which is the solid diagonal from the electron spot here shown in yellow to the positron spot, which is on the other side. So let's see here. So we discovered this angular momentum is an intrinsic property of things in the universe. Point 4, detailed account of the motion mechanism provides a frame-by-frame steps involved in all particle motion. Excuse me. Figure 5, point 5, to make our universe interesting, we need a lot of complexity and variability. Thus, the electron has 2 to the 6 states, and the proton, or hadron bit cycle, shown here, I call this the pro version, that circle I showed in the previous slide. Here, this circle I've shown in the previous slide, we could call that the home version. But you're all pros that are listening in today, so we'll go with the pro version. Has 2 to the 42 states. Now that's a lot of complexity possible. You can see right here in this, there are only 6 locations in these 3 spot units in the electron spot. So, but still, there's a lot of complexity there. That's 2 to the 6 possible configurations of an electron. So let's see. So we've made our universe interesting, and we've done so by noting that there's a whole lot of complexity possible. So we're well on our way to making a universe. Let's continue and see what else we can do. With knowledge of how things move, the motion mechanism, we can add a new law of motion to the universe. Objects move toward higher energy density, stated in just ordinary words. Now, here's a motion which we can denote as dx of an object, and here's a higher energy density here, which means the proportion of quanta loci in a volume has more one states than a lower density has fewer one states in a similar volume. So we have 2 different energy densities. Let energy density gradient equal density 1, the high one, minus density 2, divided by the distance, the diameter of the object. Now this is going to apply to whether it's a proton, a planet, or even a whole galaxy. The same law applies. With displacement dx of 1 quanta in an area A, the motion law force then can be calculated as shown here. So we can add a new law of motion, which we really desperately need in order to make our universe. Now let's look at what happens with that law of motion. The motion law, point 8, acts to aggregate quanta, no surprise, right, into spatially separated objects. The illustration here below, to illustrate this idea, the figure below shows 2 spatial dimensions, and mountain height represents quanta density. So our 2 spatial dimensions shown here in this illustration are going to be right, left, and near, far. But the amplitude or the height of these mountains is quanta density. The red arrows show quanta aggregation direction. So let's look at these two red arrows in the upper right. Quanta will tend to move toward this peak to create greater aggregation, and quanta will move to this peak. Now, what happens there is we're leaving a relatively less dense volume of our universe, and we're collecting things in different places, these peaks where we have quantum density, which they're going to become more and more dense. So this, we can say then that we're making some galaxies here, and even groups of galaxies, if you will. And there are places between these groups which are relatively spare, our intergalactic space, which are relatively sparse, I should say, excuse me, in between. So we have this aggregation effect, and you can see it elsewhere here in this illustration. Point 9. This aggregation effect occurs at all scales, okay? In other words, there's not this principle applies to an atom, but another principle applies to a galaxy. The same principles. Let's keep things simple, okay? Let's not have two sets of principles. That just throws us off and wastes all of our time. This aggregating effect occurs at all scales, from single electrons, protons, atoms, and molecules to solar systems and galaxies. Now, excuse me while I die. Okay, point 10. Now, this extreme energy aggregation due to the motion law results in massive jets of quanta and explosions in volumes with near maximum energy density. We can simulate this on a laptop. We don't even need a supercomputer. On my laptop is where I got this data from. Here, if we start out with a huge aggregation of stuff, okay, of what the universe is made of. Some people ask, well, what is this stuff? Binary mechanics doesn't tell you what it is, okay? Sorry. They could be little bananas. They could be little teeny itsy bitty Tesla motor vehicles. They could be little tinker toys. God knows what it is, but all we know is we have some volume, and it does contain some stuff. And I call that stuff one states or quanta. No, notice when we're here at maximum energy density all over here, you get massive explosions where the final density after the explosion is over, everything is blown right out the door of the simulation. Most of the quanta leave in a cubic, in a simulation of a cubic volume, they leave the place practically empty here. And so that's where we get our supernovas, which may produce low density volumes. And these are opaque to light transmission. Okay. One of the things about a TOE is that even one thing that cannot be accounted for falsifies the whole thing. Okay. So that this is a prediction of binary mechanics that at very low energy density, light cannot transmit. Why? Because the any entering quanta in this low density area gets captured by the bit cycles I already showed you. Okay, those have to fill up to a certain degree to have any light transmission beyond that volume, so that supernovas can leave, or massive explosions can leave in the universe, can leave areas where light emitted by objects behind them, from our point of view, is not seen anymore. And that is a testable hypothesis, by I think. Oh, okay, let's go on to our next slide here. There's still more to do to make a universe. Perfect vacuum contains one state quanta and is not empty space, as I pointed out. Point 13, elementary particle formation requires a minimum threshold energy density. You notice that with our initial density at maximum here, there is no proton count. It's practically zero, okay? Because everything is just blown right out, just blown to kingdom come in a massive explosion there. And we noticed that the final density shows that we get a sort of a stable maximum proton count, or actually that's a nucleon count if you want to be absolutely precise. But it's just called a proton count here in this illustration. Some of those protons could be, in fact, neutrons. And we go down and we see that there's a threshold for creating protons in the first place when we get down to very low densities. Okay, the time develop. Here's something which is absolutely astounding. 14, the time development laws result in creation of 8 elementary particles which persist without motion where inertia equals 0 after cooling to 0 Kelvin. Now, what do we have here? We have the upper left here, we have the M and L bits for 3 spot units. In other words, a spot, okay? We've said that there's 8 particles in a spot, and I showed you the spot cube with its pretty colors and so forth. And you can say, well, that's just a model. That doesn't really happen. I mean, give me a break. You mean the universe is created by a cubic lattice as far as the eye can see and our best telescopes can see of these spot cubes? Well, I guess that is what we're saying. And it's a hell of a lot simpler than string theory, where you've got some 10 or more dimensions to deal with. Okay, so what do we have here? What are these ones and zeros? These are the states of the 3 spot units in a spot. If these quanta were randomly distributed in the volume, the probability of getting this particular configuration and this top row would be less than 1%, 0.006 it says here. But now look at our 3 antimatter quarks, which are left-handed, D quarks, red, green, and blue, the 3 colors. Okay, and here are the configurations. They have double the occurrence. The statistical significance of this, because we're dealing with hundreds of thousands of spots, okay, is, I mean, essentially the certainty in this is 1. It's almost 100%. So here we have nothing but the time development laws of binary mechanics creating these 3 antimatter D quarks. And we have 3 antimatter D quarks. The common thing about each row here is that there's 3 quanta in the spots. Okay, there's count 3 every single row. Here are our 3 matter quarks. Again, double the expected probability, more than double, 0.128, and so forth. And down below, we have our positron, which is 3 L-type quanta, here and here. Now, where do we start? In this simulation, we started with a random distribution, what we call in computer science a random seeding of the volume in the simulation. So that in that case, what we see here for each of these should be what the random expectation is for that particular pattern. But the laws, the equations of binary mechanics alone, when allowed to operate, actually within only a few dozen ticks, a few dozen cycles, create these particles. So that what we have in binary mechanics are the time development equations are really the creation equations of our universe. This is just an astounding result. I could not. I have to speak as an observer and not as the principal investigator here, because some of this stuff I couldn't even believe myself. I mean, this is almost beyond the pale. This is just incredible data. Okay, the time development laws also determine the minimum energy density required, or the threshold, for creation of each particle type. We can talk about the electron has the lowest threshold, so at very low density areas of the universe, the first particles we're going to see are electrons. All right. Then the next level is your protons. Now, here is our uh, expected value, EXP, which is shown in the lower right. If only random distribution of the quanta were to occur, these are the values that you would get. Way up here at zero point 0.2 one state bit density, or one state quanta density, as I'm calling it these days. The three curves here are different orders of the 4-bit operations, which are central to the time development laws. I call them bit operations. These are analogical to, in the old-fashioned quantum mechanics, to what are called operators and wave function operators. Okay, that's what they call them. So I'm just, by analogy, calling these bit function operations, and there are 4 of them: scalar, unconditional, vector for V, and F for the strong force, which is involved in the bit cycles that I showed you. And the 3 different orders shows you that, for one thing, the threshold is very low, and that the SUVF order creates particles of matter particles of the right-handed d quarks, proportion to maximum, more than the other 2. So it does matter what order the equations are applied, and that's equation 17, which specifies that order. That's still a hypothesis at this point in time. As far as I'm concerned, that seems to be the best guess, but in my opinion, it's not been proven. So if you can come up with an actual demonstration that the one and only correct bit operations order is this one, that's probably worth a half dozen Nobel Prizes, to be frankly honest with you. So there's a little homework assignment, assuming you just want to really go down in history and physics. Okay, now 16. The proton-hadron bit cycle aggregates quanta, one states, in adjacent spot cubes. This is a fundamental principle of nucleogenesis in nuclear physics. Remember, I showed you the 42 location proton bit cycle, 3 actually, which correspond to these arrows here, the black arrows. There were 3 areas where that bit cycle of the proton actually ventured into neighboring spot cubes, and those are the one above, the one to the left in the z dimension, and the one to the right in the x dimension. That would be this arrow, and that shows you that if you have an energy buildup, in other words, an increased number of one states in a particular proton bit cycles, it would favor distributing that energy to neighboring bit cycles in these 3 directions. Now, if we flip the cube over and look at the other side, you'll notice, if you go back in the talk and replay it a little bit, you'll notice that the proton bit cycle does not contain the positron spot, which is 000, this gray one, in its spot cube. It's not there. So if we flip things over, we notice 2 things. That positron spot, which is at the solid diagonal opposite to the electron spot of the spot cube, can share with the right-handed excuse me, the left-handed antimatter quarks, which are the light pink or the red, light green, and light blue shown here. These exchanges can take place. And quanta in that positron spot, in the spot cube, then can add these additional directions of distribution of energy when energy builds up within the spot cube to distribute it. And where is it being distributed? Is it just being thrown anywhere in the simulated volume? Like, let's take a deck of cards and we'll throw this one over here and we'll throw. No. It's distributed exactly to the neighboring spot cubes. This is a foundational principle in nucleogenesis in nuclear physics. Basically, everything we know about the periodic table, the isotopes, which are stable, those that are not stable, and so forth, is based upon this foundational principle that you're seeing right here, in my opinion. Okay, 17, aggregation of quanta by the proton bit cycle results in atomic nuclei, as we've been talking about, with higher atomic numbers included in the periodic table of elements. You see how we're building our universe. Now we've got a whole bunch of elements. Wonderful. We're well along the way to having a universe finally. And their isotopes. And secondly, determines the relative stability of atomic nuclei configurations. So what do we have here? It's amazing what you can do with just a laptop, okay? And the free software which you can download from the Binary Mechanics website. You can look at the proton-electron distance, which is output to the files, which are created when the simulator runs. Okay, now below the proton threshold, which is right around here, you remember I was saying it's less than 0.1? It's down here about 0.07 or 0.06. Around there, we start to get our first protons, which basically are hydrogen atoms, okay? Our first neutrons start to appear. You notice that in the proton bit cycle, the electron spot is empty. It's not there. Go back and look at it, the 42 locations. There are no quanta in the electron cycle. What if quanta entered the electron cycle in a proton, in a spot cube that contains a proton? Well, you have our first neutrons appear at somewhat higher threshold. Okay. So the idea of thresholds is very important. First step drop in the distance, the proton and electron distance, going down all the way to here at about 0.06. About 0.6. This is a stair-step distance reduction, which indicates, in my opinion, formation of neutrons and nuclei that's occurring here to create low Z atoms up to higher Z atoms, or higher atomic number atoms, I should say. What happens here? Above about 0.6 energy density, we start to split the electrons from the protons, and we're getting this increased proton-electron distance, which implies ionization. Out here, we have our lepton quark soup. If you go over to CERN, they'll call this wrongly the quark gluon soup. It's actually, if you look at the data, there's actually more leptons there than quarks. Okay, so the proper name for it, which they apparently don't know what the proper name to call it is really the lepton quark soup, where there are no clearly defined particles at all. It's just a high concentration of one states, a high concentration of energy. So we're almost there to make our universe. This is exciting. Okay. 18, a further major aggregation step is formation of molecules. Okay, I'll leave that to the chemists. They've done well describing processes of molecule formation. Biologists then, point 20, added shock and awe with huge molecules in DNA and proteins. In other words, we're not only creating a universe, but we're creating with binary mechanics and its equations a universe that has life in it. As far as I know, this is the only cosmology that includes life in a credible way. 21. Failed gravity theories ignore all these clearly defined aggregation steps that I've talked about. Summary. Start with the best theory of everything and get everything. That's the summary of the talk. Part 1 is the theory of everything. Part 2 is let's get everything. Thank you. I guess I'm done. I have some more slides, but I'll stop there. If questions or discussion move toward those slides, we'll show those slides. Like, for example, I have the slides for the equations of binary mechanics.
I hadn't quite come, Jim.
Here.
Sorry.
Yeah, you see.
To the stage that I would give you 10 to 15 minutes as you requested. But if you want 10 to 15 minutes more, you can have it, but perhaps no more. So if that's okay. Do you want more time?
Okay. I'll go to the equations since I refer to them a lot.
Okay.
For your cosmology, you need two things. You need to define a system state. Obsolete, old-fashioned, 20th century quantum mechanics does that with the wave function, okay? But that is based upon the theory that space and time are continuous, which of course is now, in my opinion, an obsolete idea. So our postulates for cosmology has to include full quantization. And we do the three dimensions here of energy, length, and time. Now, these values define a unique point in a three-dimensional space of energy, length, and time. There's only one point in that space. That's these values shown here. There's only one point. And by the way, you mathematicians out there, prove this. Use the equations of binary mechanics and the derivation of the constants that I showed you earlier, and prove that there's one and only one point. And so there could be no other values. People talk about the Planck length and this, that, and the other. But you see, those lengths of Planck, those so-called Planck lengths and time and what have you, and mass, are based upon unexplained constants, such as the speed of light, electron mass, and so forth. So you have to explain those constants first. And so full quantization gives you a single point, which I believe there is only one possible point that solves all of the equations, which I've shown you in the constants derivation tree in this talk. Now we have questions, equations 1 through 6. And here is our quantization of energy. It's actually two equations, m equals 0 or 1 and L equals 0 or 1. The bit function is the collection in any volume from a single spot on up to the universe of the values of the M and L bits in all spot units, in all spots, in all spot cubes, which each one can equal 0 or 1, and there's three dimensions. That's our bit function. So there's the mathematical definition of that. It's sort of easy. Next, we have the spatial frame has integer coordinates. And we can talk about odd and even. It turns out that odd and even turns out to be very, very important. So that's what equation 3 tells you. It's just simply the coordinate SI modulo 2. It is either odd or even. 10, well, that's a 0. That's even. 11, that's odd. And so whatever your coordinate is, it's either an odd or an even location, which can then define values of what I call parities. And these parities can be used to determine the sign of the M bit in terms of what we measure in electromagnetic phenomena. The sign of M shown here, and this simple equation gives you a plus and minus. And the sign of our so-called magnetic monopoles, the L bits, here can be going to the right or to the left. And those are our 6 equations for the system state. When we then move on, these are the 4-bit operations, which are analogical to the operators in 20th century quantum mechanics. We're now in the 21st century binary mechanics, of course. And these are the equations for the unconditional bit operation, which just means that the bits shift and move one way or the other in a direction that the L type loci point, and that's an unconditional bit operation. And by the way, this bit operation explains the weak interactions, which are wrongly thought to be some sort of electromagnetic phenomena, but in fact, the unconditional bit operation explains all of those. Plus, for example, even here on Earth in our nuclear explosions, okay, it's the unconditional bit operation which moves stuff with tremendous force in all directions, and you know, we talk about, well, we're splitting the atom or something. Well, yeah, but actually the unconditional bit operation is what really gives you the explosive force coming out. Okay, the scalar bit operation just defines the fact that a neighboring M bit can can cause motion in its neighboring M bit. Okay, and that's your scalar bit operation. The vector bit operation shows that the magnetic effects, and the strong bit operation just shows you the transfer of bits in the bit cycles from one spot unit to the next. The strong bit operation occurs, if you look back at it, only within spots, okay? So that's the only place you're going to see the strong bit operation. And those are the 4 operations. And then, you know, we have a certain order of these operations, which I favor now the SUVF order for these operations, but that is not necessarily nailed down. In other words, someone has to come along, and perhaps a team of people, and actually say that this must be, since these operations don't commute. In other words, if you change the order, you get different results. I already showed you an example of that, where the SUV created more particles than 2 other options of bit operation or order. So they don't commute. So that means that only one can be the correct, physically correct one. And the person or persons who nail that down are going to be remembered probably forever in the annals of physics. And so I'll just throw that out for you. I probably should stop here. I just have a feeling I've talked too long. Ian, hello.
No, I don't agree with that, Jim. You're only 4 minutes over the average of 1 hour. So, you know, if you wish to wrap up, that's fine. You could take up to 10 minutes more and we wouldn't complain. So it's completely up to you.
Well, I think
I will give you time to summarize at the very end, of course, as well. So do you want maybe 5 more minutes just to, you know, finish?
No, let's just, I mean, I've just in about an hour created a whole universe from 17 equations. I think, you know, that's something to talk about. So why don't we chit chat about that and criticize it? In order to falsify a theory of everything, and that's what binary mechanics is, because the universe, we get everything from it. All we need is one phenomena that binary mechanics cannot account for, just one. So step forward if you got one.
Just as we're starting the discussion part, Jim, uh, is it all right if I take down the slides? We can bring them up if you want to relate to any specific point.
Yeah,
In,
take them down. Sure,
yeah,
you're the
okay.
boss, man. You're the
But I'm
boss. Go,
acceding to
go,
what the
go, go
audience
ahead.
wants. I'm not a dictator, hopefully. Right. Well, okay.
Well,
Well,
tomorrow I'm scheduled in the cosmology group headed by Harry Richter to present some slides on binary mechanics cosmology, which are not these slides, but I'll be presenting some more slides tomorrow in that session. So I don't know whether I should go into that now. I'd rather just have some discussion or whatever.
yes. Well, that's the norm. So we'll do that. We have
I think if you've
30
talked
minutes.
about an hour, let some other people talk.
Yes, quite so.
Yeah, I mean, I have great
Well,
respect for the people in this group, uh, and I've learned a lot from their thoughts, and so let me learn something and listen to somebody else for a while.
right. Well, I'd like to start the ball rolling by just expressing my appreciation for your talk. I have heard you talk a number of times, as indeed others have, but you've always got some new angle and some new information. Um, I mean, this whole business of from a TOE coming to a cosmological general explanation. You're building up the elements and then the molecules and onto life processes. That was quite impressive as well. And I liked your images. For example, your geometrical image with the mountains and the various curves and all this sort of thing. There was one question raised, I think, maybe by Quest Iron, and it just prompted an idea. Just perhaps before we go through the questions quickly. You see, it could be said that the model of discreteness of space and so on, seems to have borne a lot of fruit and has derived for you many fundamental constants. But I think the question is, and maybe this is what was being got at, is there any sort of hard evidence to rule out continuous space and substitute discrete space for it?
Well,
It's true, apart from being useful, let's say.
that's a that I think that's a tremendous question, good question. In terms of, I'd like to hear other people's
Okay, well let's.
idea of is there something what going on a different track of of full, what I call full quantization, was the finding, if you will, that all of those theories that use the idea space and time are continuous, that is, mathematically speaking, we're going to have real number coordinates and so forth. They all have paradoxes. They all require miracles. They all require magic. Imagine, say, general relativity. You're going to have, they all require additional dimensions, which cannot really be falsified. And so if you have a theory that can't be falsified, right there, you've got a little bit of a problem. Now, but I'm sure other people might have better ideas than me on this. What happened with me is that a former MIT student named James S. Hughes came over to my house, and like many nerds, I have a blackboard in my kitchen. I had at that time, in 1993 approximately, a blackboard in my kitchen, and he said that if you take a pair of Dirac spinor equations and relativistic spinor equations, you get an 8 by 8 matrix equation. Okay. And if you rotate the spinners, you get a cube. You get the vertices of a cube. And he knew that I had done a lot of computer programming and matrix algebra and so forth, and advanced statistics like factor analysis and eigenvalue calculation and all of this, which by the way, the particle physicists steal from statistics the factor analysis, the eigenvectors and eigenvalues. That's just all statistics that they stole the math from to try to represent their particle states.
Using
But
the German
anyway,
term.
James Hughes presented this on the blackboard, and I looked at it. I said, "Gee, I can't find anything wrong with this." Now, I love to find things wrong with things. All of us do, I suppose. And so I couldn't find anything wrong with that. And so then we're talking about really each of the 8 component solutions to this pair of relativistic Dirac equations, which, by the way, were used to discover the existence of the positron, or postulate the existence of the positron as the antiparticle of the electron, which was later discovered to be, in fact, that there were such particles. And at any rate, so what Hughes was saying was that really we have 8. We don't have 8 complex values for each spot in space, as Dirac was saying. What we have, in fact, is a matrix or grid of 8 adjoining spots in a cube. So I took this from Hughes. Now, and then I said, well, what is the size of these things? There has to be some particular size if this makes any sense at all. And that's when binary mechanics was formed. I said, well, let's just go all the way, what we call full Monty. That means you take all your clothes off. I looked that up on Google one time. That's what full Monty means. And so I went full Monty and said, we'll just quantize space, time, and energy. We'll just do the whole thing in one shot.
So could we perhaps, Jim, with your permission, just spend a few moments, not very long, just dealing with, because I think there are only a few questions, very, very briefly, and then we'll come back to some of those points when we get to the more detailed discussion. Will that be all right?
Sure, absolutely.
Because some of these things are just one-liners, and I don't know if you have anything just quickly or not. Question, he says, could an empty space exist underneath a 3D grid of spot cubes? So he's talking about maybe empty space as distinct from, space, non-empty space.
Well, you're talking about a different space. I don't know what...
is that outside your Ken?
Empty space underneath a 3D grid actually means? I'm sorry, I guess.
Okay, I don't think Jerry.
Well,
is in the
one of the things that you'll find in all of the theories that I believe fail. One of the things you'll find in all the theories that fail is that they're postulating a 4th or even 5th, 6th, 7th, and 8th and 9th dimensions. And binary mechanics gives you an entire universe with just 3. Okay? So if parsimony means anything in science anymore, which apparently it doesn't, because when all of these theories like special relativity, general relativity, even Newton's theory of gravity fail, people then immediately jump on the barge and say, let's make it all more complicated, and then it will succeed. When in fact, they're going in the opposite direction. They have to make things simpler, in my opinion.
So this is perhaps the basis of some of the discussions, some of the questions which were prompted by Question's point. He says, is this the only theory, though, were there observations or experiments which confirmed much of this? So maybe that's another question put to you. I mean, it's a very useful model, and you have good results.
The observation is, Well, one of the main things is that we've been able to reverse engineer the universe to the extent that we can derive from what I call the primary constants, M, L, and T, that I showed in the slide there, and use use those values to derive all of the what I call now secondary constants, like speed of light, um, Planck's constant, electric charge, and so forth. Absolutely nobody has been able to do that. And so that if your theory, you can start to make a list of all of the things which tell you you have a bad toe, because and there's hundreds of them around, and there are major issues that remain to be solved in binary mechanics, as I pointed out. So there's no need for people to go second class. They can go first class with binary mechanics and make some real discoveries rather than tinker around with this idea that space and time are continuous and continue to fail. Okay.
Yeah, I know, Jim, you've frequently made the statement that the mainstream has had chances to, get to the bottom of all this, and they've singularly failed. They've missed their chance. By the way, I must make an apology. We're having an easy time in a way.
Correct. So that,
sorry, Jim.
It's sort of like.
Sorry, may I make an apology first, please? We don't have that many questions, but the reason for that, I've discovered, is that the Facebook has not enabled us today. So people who, ordinary people who don't go through the green room, but come in through Facebook, won't have succeeded today. However, the YouTube is working. So I don't know. I've just sent an email to David de Hilster to see, can he sort that out? Because I think it's something that has to be set up in the administration. So just my apologies for that. You'll have to watch the recording. But there were one or two questions from Cornelis, who is in the green room, and I may bring him in a moment, but he has specific questions, so he's followed my request just to highlight it. He says, Jim, are there not, in your model, maybe represented by a multi-dimensional array with dimensions well beyond 3 when you consider your fundamental constants? But you say no, do you? Are there not in your model?
The fundamental constants correspond and map directly to the units of measurement used in physics since forever. Okay, mass, length, and time. Those are everything is defined of that. And so I don't know whether a theory would be the thing they call the irreducible.
I mean, that's an ordinary
mathematicians
dynamic.
Have.
You're breaking up a bit, and I think we're speaking at cross.
What was that, Ian?
Yeah, I think you're breaking up, and when I say something,
an ordinary dynamic.
Yeah, what I was. Yeah, there you got that. In ordinary dynamics, what you say is true, but if you extend it to electricity and magnetism, well, you have to bring in things like current or charge, let's say, more basic charge. And, similarly for light, you'd have to bring in maybe light intensity, lumens. So I don't know.
Right.
That's
well,
Corey is thinking of.
All of that is included in the equations. Okay, the system state equations.
But I didn't say
define what's called a fractional charge, which is 1/3.
A charge analog of the MLT cubes that you showed.
I'm not hearing you, Ian.
Yeah, I don't know what's gone wrong. Can you hear me? No.
Well, the M-type quanta have a property which we call charge and also color, and The equations for that are given in my paper, Binary Mechanics Postulates, and I showed the equations also during this presentation very briefly. The
Can you hear
L-type
me?
bits seem to be related more to raw energy or radiation. That's why I call them lights. Again, the letter L for the L-type quanta. But whatever words we use are just analogies to help us think about what the equations are saying. Because all of the results I showed you are from application of these equations. The computer simulation doesn't know what we call a one state, whether we call it a quanta, whether we call it a little banana, or whether we call it a little Barbie doll. It could be anything. But the so I use some of these terms just to help by these equations relates to other areas of physics, such as the existence of charge.
Jim, yeah, I'm going to bring you up, Nick, not only because you're asking, but can you hear me? Because Jim can't hear me.
I can hear you, yes.
Okay,
I
so
can hear
everybody
you,
else,
Ian, but sometimes you break up.
yeah, okay. It seems to be a problem with just our communication because I know we were talking over each other.
Hi, Nick.
Anyway, Nick, welcome. Have you got any enlightenment or questions for Jim or any
I
opinions?
have 4 points, which have all of them have good and bad. First of all, I wanted to congratulate James.
I see Nick on the screen.
Yes, he's on the screen.
He may not be hearing me. I wanted to congratulate James as he and God are the only two so far that have been able to create a universe from scratch. However,
Sorry, who's the first one? What and God?
James.
Oh, right. He, yeah.
But the bad part of that is that if God and he don't agree, then he's wrong. But if they do agree, then he's going to be accused of plagiarism.
Well, binary mechanics is an effort to reverse engineer.
Yes. Second point is I see 3 places where you have stubbed your toe, but hopefully those points will help improve your theory of everything. On your chart, I think it was number 14 where you showed that the left and right quarks were.
Nick is breaking up.
Yeah, Nick, I think Jim has a problem hearing any of us.
Okay.
Which is a problem.
Maybe you can help. Where he said that the left and right quarks had twice the chance of another random state. Actually, unless he put up the wrong numbers, it was 20 times likely that the left and right quarks would appear, which makes his theory 10 times better.
Did you get that, Jim?
Well, I have to look at that. I have to look at that slide again. Thanks, Nick. If I misspoke on the ratio there, that's my mistake.
Yeah,
I missed your first
part,
point because you were breaking up.
Okay, I'll talk to you about that later. The third point is about an absolute frame. And to me, that introduces a level of abstract mathematics to your theory that's incorrect. Because the one thing I agree about Einstein is that all physics is local. In other words, for any phenomenon, it's a case of one or more physical entities interacting with another physical entity. And it's not not frame dependent. And the GPS system really strongly supports that. There's no universal absolute frame. Physics is local and is the interaction of physical entities. And any view that's different than that just tends to make it abstract math and blocks out what's happening physically. Okay, now my fourth point is that supernovas and strong explosions.
Most of what Nick said, I could not hear. But I did hear that he said there's no absolute frame, and he was citing GPS and so forth. Let me say this. That's a great reason why you need to drop this theory that space and time are continuous, because you get into these circular go nowhere arguments. If you quantize space, quantize energy, space, and time, as binary mechanics does, have an absolute reference frame. How would you do that? How would you have? How is that possible? How could that be?
Okay, that point
that
is
you
not
would not
relevant.
Have
that point is not relevant to my point, because my point depends on the GPS data and not on the theory.
What was your point?
I got that, because it appears we're talking over each other because of the.
I didn't hear what your point was.
Did you get what he said, Jim? About GPS,
my point is based on GPS data, not on continuous space or time. In fact, it's based on quantized time.
There's obviously a problem because, I thought something had gone wrong. It's impossible to.
Well, Nick is coming in and out.
And vice versa. It's not working at all. I'm sorry. I don't know what's happened with you. And you're freezing up a little, Jim.
I don't. Yeah, I don't see how I can respond just by the. But I did gather that he's questioning the existence of an absolute reference frame. And I have a simple question. If you quantize space, energy, and time, as binary mechanics does, how would you not have an absolute reference frame? How could that happen? Explain me that.
Oh, you have local frames. Non-universal. You have
half of what Nick is saying is simply not being.
I don't have any frames. I get rid of frames. I just have physical entities interacting. Okay. Final point, and
that's the limitation. That's a very severe limitation for making advances in physics, in my opinion. For example,
let him make a final point, and then we'll
have an absolute.
See, he doesn't hear what I'm saying.
You have no way to define the ground state.
Jim, can you hear what I'm saying? Can you hear me?
Yes.
Yeah. If you would just
I can.
Let Nick make his final point, and then we'll cut him off and we'll let you come back. Is that okay? It's impossible at the moment. We're going back and forth. Nick.
Yeah, I may. Ian,
if you can hear Nick without breakup, you can rephrase his point.
Okay. But can you hear me then? You see, if I rephrase your point, Nick, it's the same problem, because Jim has a problem hearing us totally without breakup.
Okay, I'll try and put some of my comments into the chat, but let me just state my fourth one, since it's pretty simple. Jim referenced a supernova explosion coming because you go below some level in density, where in fact the empirical evidence is that supernovas occur because of stars collapsing due to the gravitational pull and get into a super dense state and then explode.
Some people say there was a delay of 10 seconds, but I think it's more fundamental than that.
Yeah. Okay, I'll put that in the chat and we'll
private chat.
Thank you.
Oh, okay, thank you very much, Nick. Thank you very much. So, Jim, I think Nick is going to type in a couple of lines there, which might be the simplest thing to do. Okay. Now, while he's doing that,
you see, now I'm hearing you perfectly.
Are you?
Yes, I'm hearing you perfectly now, Ian.
Well, maybe we've solved the problem, Jim. There seemed to be a delay in the line, but also I'd be talking and you wouldn't take any notice of me. So I'm sure you couldn't hear what I was saying. But it seems maybe it's fixed now. Can you hear me? You're not responding immediately, though. No, you're not responding. So I think this is still a problem.
Yeah, I see that you're breaking up. The problem that, from what I can gather, and what Nick was saying, is that his whole approach is suffering from the fact that you don't necessarily have to be logically consistent with the theory that space and time are continuous, because you have paradoxes, dualities, magic, miracles required for it to make any sense. In binary mechanics, we don't have that luxury. Everything must be logical. Everything must flow. There's certain conclusions which you cannot escape. If you don't have, for example, and I thank Nick for bringing this out in what little I could hear of what he was saying, because he's a first-class intellect, and I don't want to try to paraphrase him when I didn't really hear everything he said, just little phrases here and there. But if you don't have an absolute reference frame, you can't even begin to study what the ground states of particles are. If you're talking about some GPS frame or ECI frame of the rotating Earth in its orbit and all of this, you have no way to really get down to the fundamentals of what the actual composition of these particles is or are. Well,
I think you might have been referring to
composition. Yes,
a de facto absolute frame, but in the local sense. Yeah. Anyway, I don't think you heard what I said. Okay. While he's maybe writing a few things down,
repeat that, please, sir.
Say again. What was that, Jim? I'm sorry. The quality is just disimproving so much that we may have to terminate this talk a bit early. It's just impossible to get ourselves heard. But anyway, just before that, Cornelis, are you there? No, he's mute, and there's no because he had a couple of questions here. Oh, there you are. I couldn't put your questions up because of the audio problem, so I curtailed it. So maybe you'd like to raise those questions and perhaps give your own take on. I assume you can hear me perfectly, by the way, Cornelis.
Yes, I can hear you fine. Can you hear me all right?
I can hear you perfectly, yes.
Yeah, my question goes way back in the earlier times where James was comparing his theory to the multiple dimensions. Excuse me, to the multiple dimensions of quantum theory and string theory and that. And basically, I look at dimensions, and I think they when they talk about dimensions in physics, they're not talking about strictly the Euclidean, up, down, left, right dimensions. They're talking about properties. And in James's program, for instance, in his computer program, his cells are simulating the status of any particular cell with a multiple dimensional array. And the number of elements in that array probably far exceed just the three of X, Y, and Z location. They also consist of the amount of mass, the time. There's multiple things that you have in that array that are basically, in a programming language, they call that a multi-dimensional array. And in the same thing in physics, from a physics standpoint, each property that something has, a location has, or an item has, is considered a dimension. So in that sense, both your program and quantum mechanics and string theory have multiple dimensions beyond just three. Does that make sense? I mean, is that correct, Jim, from the programming standpoint too?
Did you get that, Jim?
Well, in fact, none of the variables that you mentioned in terms of mass and so forth. Well, actually, the program only uses 1 states or 0 states. There's no mass assignment there in the equations. You can look at the equations and find mass in there. It's not there. Okay, so
that's not the
in
point.
everyday
The point is, if you had just a one
language,
state,
you could say that what we're which can.
You see, there's no impoliteness here, Cornelis. It appears that, it's just the audio problem looks as if we're talking across each other.
I thought perhaps if James turned off his video, it might improve his sound, but I'm not sure if that's the case. Sometimes, if he's over.
Bandwidth. Did you hear that, Jim? If you turned off your video.
To respond to what Cornelis is saying, in the equation.
Yeah. Okay, that's one point about a different terminology in dimensions. Did you have another point before we bring it down and we deal with Nick's point, which is written?
I think basically that was my main point, was just distinguishing, the purpose of what a dimension really is. That's I think James is not quite catching that.
No.
But I've done programming before, and I know you have multiple dimension arrays, and it's far beyond, just 2 or 3 usually. Okay, that's all I'm going to do for now.
Yeah, sure. I think he'd be happy if you wanted to pop him an email or something just with a line or two. So what I was saying and you couldn't get because the audio problem was this. I think he'd be quite happy to deal with that. So if we could leave it at that, Cornelis, for the moment anyway. Thank you very much.
He also spoke of gates and other things that were between his elements and that are just, kind of like a mysterious thing. And those gates would themselves, whether they're off and on, would also take up an additional dimension in his model and that. So there's so many things that are kind of hidden there, but there are more dimensions than just 3 spot cubes. Anyway, that's it. I'll let it go for now and see if we can get somebody else on.
Multi-dimensional model. Okay, thanks very much, Cornelis. Now, so you can probably read this, but the people participating.
Okay, I'd like to respond to Cornelis's point.
Which point? The one about dimensions?
Let me respond to Cornelis, if I may. That you can. Some of these simulations involve hundreds of thousands, even millions of quanta. So that you could say that there's a million dimensions if you want. And so I would invite Cornelis, if he chooses to say that we're not dealing with events in a 3-dimensional real space, okay, physical space, and not some mathematical idea, to pursue that approach. I mean, and see what he gets. I'd like to see what results or conclusions he gets from that.
Okay, well, perhaps this is
Do
something
we learn anything about physics from
on
that
a
sort of
one-to-one basis, because it
approach?
could be a bit of argumentation about terminology. Can we come back to Nick Percival's point? I think you can probably read it yourself, Jim. I'll read it out for the benefit of people who don't have access to the green room. Jim, you were stating that when you went below 0.7 or something, that would cause a great explosion and liken that to a supernova. However, a supernova seems to... Let me read it, Jim. However, a supernova seems to be caused by gravity, causing a collapse that causes ever greater density, and that causes a supernova explosion. Have you any reaction?
That's entirely in agreement with what I was saying. He got the threshold of 0.7 wrong, but aside from that, yes, what the graph that I showed is that however it occurs, when the aggregation effect, you could say that everything I presented in the some 20 steps in my presentation in creating a universe, that everything would clump up into one big mass if there weren't these explosions. Okay, so that the explosions sort of resets the system so that everything just doesn't collect into one big mass in the universe, and the universe keeps humming along as we more or less see it now. And so that I have nothing to quibble with aside from that. He says the collapse that causes ever greater density, and this causes a supernova explosion. That's exactly what I was talking about. That when you get by the aggregation law of motion, okay, that I described, it's not gravity, by the way. Gravity is just a word that is used to describe that. Binary mechanics provides you with the actual events that are occurring. You can call it gravity if you want. But gravity is not a force, as you can see in the equations of binary mechanics. It doesn't exist as a force. There's not a single equation about gravity in the 17 equations that create a universe. But I agree that yes, when you get excessive, very high concentration of quanta at high energy density levels, the explosion is so violent and so dramatic that in my little computer simulations, virtually everything, all the one-state quanta are blown right out of the simulation. Okay? And
okay.
The simulation can be run in different ways. One way is that.
So I'm sorry, I'd like to give you a few moments to summarize at the end.
Can you hear me, Ian?
Can you hear me? Yeah, it's very, very unsatisfactory. There's one more person in our green room, Carl Reith. Is he there? His microphone is mute and there's no video. No, it's just if he was there, I'd give him an opportunity of coming in. There's no response. So if you'll all permit me to interrupt the proceedings for 2.5 minutes.
Nick has said.
Jim, we'll come back to this to summarize. If you permit me just to interrupt the proceedings to play a little video, it's just about the funding mechanism of the organization. So we'll come back to it just in a minute or two. So here it goes. It's the president of the CNPS just asking for maybe increased support for running the show.
Hello, everyone. I'm David D. Hilster, president of the John Chappell Natural Philosophy Society. During the past 2 years, we have used annual fundraising drives in order to keep our organization's presence alive and well on the internet. Both years we have been successful in that the monies collected have been enough to keep us afloat. This year is our third annual online fundraiser, and once again, we are counting on your support. But first, I want to thank everyone who pays their annual memberships through our automatic online system. Your support is vital and provides us with important funds to keep the CMPS afloat. Hopefully, as we continue to grow, we will be gaining more and more automatic memberships so that these fundraising events won't be necessary. But we are not quite there yet. This year, we will be implementing several changes to our online system, several to save money and lower our annual expenses, and another to better our discussion platform. First, we will be moving our websites and databases to another server that has graciously volunteered to host us at a much reduced rate. It currently costs us $1,400 a year for our dedicated server, given that we need complete control over our own software. The new server will give us and allow us that control, but only for $250 a year. Second, we will be moving away from BuddyPress, which is a Facebook-like plugin for WordPress, to using Discourse. BuddyPress was an interesting experiment, but the upkeep of the plugin and its general design don't really fit what we need. What we need is a robust and well-accepted discussion forum, and that is why we'll be moving our online discussions to Discourse. It costs $20 a month, which is half the price of BuddyPress. I think those currently active in our online discussions will find this new platform much more enjoyable and functional. Third, we are moving to a free version of Overleaf, which eliminates a $33 monthly fee. Overleaf was useful for us when we were publishing our own proceedings for conferences, but that is no longer needed. Our goal this year is $2,000, and I hope we can reach that goal. Whatever amount you can donate, it is greatly appreciated and needed. Your membership and donations are vital to keeping our online community of critical thinkers alive and well. To donate, go to fund.naturalphilosophy.org. That is fund, F-U-N-D, .naturalphilosophy.org. Thank you, and keep up the amazing work that is driving science forward.
Okay, my apologies for that, but it's sort of business. We can come back now to wrap up. However, as I'm sure you've seen, Jim, Nick has a second point here, which again, for the benefit of people who don't have access to the private chat, I'll read out. So Nick Percival says, my view is that frames are an abstract math construct, whereas a physics view is the interaction between physics entities. So velocity should not be discussed in relation to a single frame, but rather relative v between entities. And he says in parentheses, this is not endorsing relativity. For example, Lorentzian theory uses v with respect to the ether frame, whereas it's better to reference v of an object with respect to the local physical ether it passes through. I can read and respond to Nick's comments. Yeah, thank you, Jim. Would you like to do that briefly? Can you hear me, Jim?
Yeah, there's nothing in binary mechanics that says you cannot define. Yes, I can.
There's a delay.
Can
Go
you
ahead.
hear me, Ian? Can
Yes.
you hear me, Ian?
I think there is a delay of about 10 seconds.
Okay, if you can hear me, there's nothing in binary mechanics that says you cannot or are forbidden from defining any frame that you want to define for any particular purpose to collect data or conduct experiments, etc. All we're saying is that it's an inescapable conclusion of the postulates of binary mechanics that there is an absolute reference frame, and that without that, we would not even be able to define what the ground state that I showed you in the slides of certain particles are, because they wouldn't be respect to the absolute frame. Okay, we can assume that things here on Earth are in motion with respect, so that we're never really going to see the true ground state of these particles that we can see with the assumptions of binary mechanics. And it all gets, the big divide is whether we want to work with a theory that space and time are continuous and put up with all of the miracles and puzzles, paradoxes, dualities, and so forth that it entails, or do we want to have a clean slate alternative approach? The alternative approach was suggested to me by James Hughes in his analysis of the Dirac spinors. And I just built from that in saying, let's quantize everything, because there's a number, it's sort of like education, where we have to learn arithmetic before we can really understand algebra. If you don't know how to multiply, add, and subtract numbers and divide numbers, you're not going to be able to really solve algebraic equations for the unknowns, because you need to use arithmetic to say, we're going to continue with an assumption of continuous space-time, which has failed us 7 ways to Sunday in virtually every way that we can imagine, and just skip over the fact that these so-called fundamental constants like electric charge and Planck's constant and speed of light and so forth, we don't know why they have the values that we have, but we require to use them as input parameters. It's sort of like saying you're going beyond what you need to do is to solve that problem first, and then move on after that. No one has been able to solve that problem except with binary mechanic assumptions of full quantization. So that right there, you have an incredible victory. And so that puts binary mechanics as the lead horse in the race in terms of physics research. Maybe someone else will have another theory of everything, as it were, that will derive all of these constants and derive like all of the possible particle interactions that can occur and so forth that binary mechanics has done. Then the question is this other theory another representation of what binary mechanics is presenting? In other words, if you were to rotate the coordinates for mass, length, and time, you would get a new set of laws. But if those laws are exactly the same and only different because you've made a rotation, it means that the two theories are in fact identical. Okay? Is that idea understood?
Well,
I hope.
Yeah, you have to wait to hear me, but I'm glad that Nick is going to correspond with you further on this. So, I mean, that is one good spin-off of our sessions where we're having some more private chat between people. And then if anything significant comes of that, we can bring them back and talk about it further, or maybe get a further talk on the subject. So, Jim, before I come back officially, just say a few words, if I may, and close the meeting. Is there anything else you'd like to say in summary or in addressing some of the other points that have come up in the discussion? Did you get that, Jim?
I just heard somebody say. No, I didn't. Somebody said something about the discussion.
So I am going to close the meeting in presently, very, very soon. But before I do that, would you like to say anything else? You have a minute or two to say anything else you wish that has been missed. or have you said it all? I think the sound problem is so significant that we will have to. Okay, I'll assume, Jim, that you have finished for today.
Okay. Okay. Thank
And I'll bring you down, and I'll just I
Okay.
think everybody can hear me, so I'll just say a few words if I may. Okay. And if anything else comes, you can always come in contact with me if you feel I've cut anybody off or whatever. So, so it devolves upon me now, and I trust you can all hear me perfectly, to express the thanks of the CNPS very much for Jim. I know he's done a lot of work on this. It's reasonably evident from actually the amount of information he's given us and the slides. And I am also impressed how a model which he continually claims is basically one at the quantum level, it's a very minuscule thing, it has also been proved useful at the cosmological level, or at least that's what he's claiming now. It could actually be used as a theory of everything, from the very, very small to the very, very large, which the mainstream physicists, even though they claim to have solved problems and to be on the forefront in describing the origin of the world and all that, they admit that there's a complete mismatch between their theories of the small at the quantum level and their theories of the large, the sort of general relativity. So I'm impressed with Jim's work, and a number of other things haven't come out today, but maybe in previous lectures they had been adverted to. Yeah. So, for example, the fact that Jim's software is available free of charge. One can download this. One can go into the binary mechanics website, just search for binary mechanics, maybe Google that, get into his website, and you can do some of these simulations yourself. And if you're in difficulties, Jim would be more than happy, if I may speak for him, to help. He's so enthusiastic about this subject that I know he loves talking about it. And even when you get criticisms like me that it's all marvelous and it seems to work, but is there any fundamental truth behind it, like a philosophical truth, he doesn't get upset. He's quite happy to discuss this with all people. And similarly, Nick's correspondence now and Cornelis's correspondence will stimulate us further, and we'll probably bring Jim back at a later stage. And as he said, these cosmology discussions, which take place on Sunday, he'll be talking again tomorrow, I think, on that. So I apologize again for the two hiccups we've had today. Nothing ever runs smoothly. One is the fact that the Facebook people could not get in, and unless they went to one of the other mechanisms, they have been deprived of today's talk. And indeed, the recording won't be available on Facebook. It'll be available on YouTube, so you can get it that way, the recording for the CNPS YouTube channel. Similarly, the audio problem, which unfortunately I think was really at Jim's end, because we all could seem to hear each other without any of these delays. I think the fundamental problem was a delay, sort of a latency period or something. But I think there was something more to it than that, because we seem to be talking across each other. And I know we're all polite gentlemen. We wouldn't do that normally. So, please, if it appeared that I was trying to keep Jim quiet and stop him, or I was shouting a bit, it was only because of the audio problem. So we'll try to resolve those issues. I'd like to thank you all very much for participating, for your continual support of the CNPS, and for your understanding of the funding difficulties we have had, which I think we're getting over for at least this year. And of course, our speaker today, James J. Keene, who has been a great sport. He's always, he's done so much work on this that we can appreciate the level, the profundity of his thinking, and he's always happy to entertain new views. But he's also got a sort of like a good sense of humor, and he's always able to get through the nonsense and maybe give us a few points. I know that when I'm speaking or somebody else speaking, he's always giving some interesting insights and questions himself. So we've got back at him to a certain extent, but he's taken it in a jolly good stride. So I'm going to end the session now. Thank you very much indeed, and we hope to see you the next time. Good day.